industrial engineer is really focusing on a process, and more specifically, they're usually dealing with people in a process, how people, materials, information flow, and how can you improve that process, make it safer, more cost-effective, and all around just more efficient.
To me, IE is working at a system level to reduce waste, whether that be waste of time, money, energy.
IMSE to me is about improving systems, so that system can be anything from the typical manufacturing side of things that a lot of people think of industrial, but it could also be healthcare or businesses, management companies.
We consider ourselves to be the people engineers, where we try to engineer the way people interact with technology in the workplace, as well as interacting with other people.
Industrial engineering is the major that connects business and management with the engineering knowledge too. You have to have good social skills, connection skills, and good engineering background as well.
You're really understanding the entire system, including the business aspects too. You're not just limited to the technical degree. You kind of get that good background in economics, and you kind of get that background in business and see how a business works, as well as the technical field.
Industrial engineering is more than just working with mechanics on the floor in a factory. It is working on the people and the systems that work in those factories. So the skeleton behind me could be used to determine the load for a particular move on a body, and also the strain in a particular area with ergonomics or human factors that we study here at Iowa State.
I chose to study IMSE because of the versatility in the field, so you can go into any field you really want to, whether it's aerospace or automotive or healthcare.
I wanted to be working with people, to work around people, to be able to have connections, and industrial engineering does a great job of explaining how you are the engineer, you are the leader in the work environment, so you have to work with the people, not necessarily boss them around, but help them do the job more efficiently.
I worked with Dr. Stone the first semester of my sophomore year here at Iowa State, and it was a really good experience for me because it allowed me to work on my own on a large amount of projects. I was given a large amount of responsibility for my projects, and also it increased my accountability for deadlines that I was setting with the professor I was working with.
Iowa State's really well known for its engineering program and how well respected it is among the community.
They're really passionate about what they do here at Iowa State.
I chose Iowa State because of the engineering programs here, and also the wide variety of campus activities that I could be involved in to have a well-rounded college experience.
We have a ton of tutoring, a ton of hands-on labs. Everything here is very much like focused on you and your success in the future.
I want to be working in my dream job on the manufacturing floor, working with operators on a daily basis, seeing the things that I am doing to make their lives and their jobs easier and more efficient for them to complete.
I think my dream job would entail working in an interdisciplinary group, so people from a lot of different backgrounds and fields of study, just so we can have a lot of different perspectives.
So my dream job my entire life was working for Boeing as an industrial engineer. So I have that opportunity now, and I'll be moving up to Seattle in May to do that full time. So after that, I'm not quite sure what my dream job would be, because I'm going to be living it in a couple months.
Hello, my name is Cameron McKenzie. I'm an assistant professor in Industrial and Manufacturing Systems Engineering, and this is work that I'm going to be presenting with Zhouyi Zhao and Sylvia Knight, two graduate students, also in Industrial and Manufacturing Systems Engineering, and Stephen Gilbert, who's an associate professor in our department, and Nate Sepik and Kennedy Cook, who are students in our department as well, also helped with the material for this presentation. I wanted to recognize their efforts. So first of all, let me just give you a little bit of a background in terms of what this project is all about. We are working with a large manufacturing company, and this company is interested in exploring different ways in terms of how a digital twin can benefit them. And there's a lot of different pieces to the project, and our specific part of the project, and what we're going to focus for the most part on this presentation, is first of all, discovering from this company what type of needs they might have for a digital twin. And that involved talking with a lot of their employees and trying to understand, okay, this concept of the digital twin, how might it help you actually in a manufacturing setting? And then we're going to use some of those comments to then think about, okay, how can we incorporate those questions and those desire for more information into a simulation. And then finally, talking a little bit, we're not going to get to very much in the presentation on this part, but this is something else that we're working on, is how we kind of combine the simulation with other data inputs into actually being able to do some sort of analysis. So when we talked with them in terms of what they think they would like from a digital twin, there are a few concepts that came up. One is, can they help them with line balancing in order to be able to move operations from one station to another that would help them meet required takt times? Can they think about how to schedule workers better or on a kind of more dynamic element? You know, obviously they're dealing with the pandemic like a lot of other companies. Employees are absent, sometimes because of the pandemic, sometimes because of other things. And so can they quickly change the schedule of workers to deal with this type of thing? Inventory. How can they know whether they have sufficient inventory on hand? What will the production look like in a couple weeks with the given inventory? When would they need to reorder inventory based on what they're producing? And what if they're all of a sudden told that some inventory is going to be short or going to arrive late? How will that affect their production system? Maintenance. Can they think about how they assess the health of the machine? What data, what statistics do they need to collect from the machines to be able to understand what the status of the machine is, and how can that help them do better preventative, better condition-based maintenance as well? And then finally, just overall, kind of how can a digital twin help them in a production setting so that they can meet their production targets, understanding what might be delaying their productions, as well as understanding, okay, if something is happening upstream in our production, how is that going to impact production downstream? And what we kind of realized in talking to them is that a lot of these questions can be answered to some extent by Simio and using a discrete event simulation software like Simio. And we're going to talk specifically about two points in that relate to these user needs. One is simulate from a current production state that can resolve such as production, scheduling, inventory issues. And then also, how can we use Simio to help us understand the impact as well as make better decisions when it comes to condition-based maintenance?
All right, so as Dr. McKenzie said, one of the things that we were focusing on was simulating production if we have a snapshot of what this facility currently looks like. So what we have is a model of part of this production facility. And one of the things that we really relied on for this is Simio's ability to build a model directly from data. So there's data tables in the model that are bound to Excel sheets, and we use processes to allow a real-time display of status at the servers. It shows where the work in process in the system is right when you initialize the simulation, and you can do the entity arrivals via an order schedule, via event, as they are actually in the simulation I'm going to show you, or they can be randomly. So this is the actual simulation that was built. So as you can see, it's a fairly basic, just linear simulation. The entities just go through 9 different stations from the start to the end. Each station has an employee. And the interesting thing about the way that we were able to set this up is that, so we have this table that's going to show you for each station which employee is it going to use. And each of these are actually a list in the simulation that currently only has an employee on it. But what you can do is you can define lists, say, of every employee but one. Or maybe you have, okay, I know these 3 employees are all trained to do the work at this particular station. So let's put all 3 of them on a list, and then this station can use any 3 of them. So that would really help you to see and say that somebody calls off, or you end up with people needing to be pulled to do something else. You're able to see, okay, how do I cover this? If I cover this way, how is it going to end up looking? The simulation also includes different materials inventory for some of the stations. So that's also incorporated into this. You can see all right, if I've got this many parts of, say, part number 6, how far is that going to get me in the day or in the week or in the month, or until the next shipment arrives? Is that going to put us behind schedule? If you want to, like, you can also do entity arrivals via an order schedule, and that's what this table would be for. It's again bound to an Excel sheet. So assuming that the company has some kind of an order schedule somewhere, if that can be converted to Excel or CSV or any of the other data types that can be uploaded to Simio, you can bind that to this data table, and then you've got an order schedule. There's also the potential to include bill of materials for certain parts. So let's say at station number 6, I need parts 4, 5, and 7 to get something done. You can put that into the tables as well. And then the last part is actually the work in process here to show, all right, we know that there is currently a widget at station 3, and there's currently a widget at station 7. So that way, when we want to simulate from our current state, we need to have those things currently at those stations, because they're not just going to be entering the simulation or entering the line at this time. They're currently already there. And then, so I'm just going to run this for a little bit just to show you guys what it looks like. That there is real-time updating of the task status. So you can see, all right, so this is on task 3 of 9, for example, and it'll move through. And all of these servers and resources are on work schedules. And those are also something that you can define for yourself and then put in the Excel sheets. And as long as the name in the Excel sheet is the name of a schedule you have in the Simio simulation, it will understand, all right, so I know that 5-day week, for example, means that this person or the server is available from 9 to 5 with a break from noon to 1. So I'm going to show you a little bit of how we actually did the ability to update things and the process for putting the work in process right at the stations right away. So this process right here, the one that says on run initialized, is the one that lets us put the WIP right at the station. So it's going to search through that WIP table, look for where there need to be entities, create entities for those locations, and then, so it's actually pretty straightforward. It only runs once on startup, and that sets up all of the WIP for the system. And then to do the status updating, there's a state variable for the status of each of the stations. And within each station, there's a process that runs to do the processing time. And that process is going to be like this big long thing here. So you seize the worker, the resource that you need, you execute all these processes, and these individual processes are the ones that include an assign step for the state variable. And that state variable is then what is shown in the status labels here. So what we eventually want to be able to do with this is use this as a digital twin to help people make decisions. So if we can see, all right, from the current state, where are we going to be in 2 weeks? That's really going to help in deciding what we should do, especially if we have issues such as maybe we've got late orders, maybe we're running out of inventory for something, maybe there's employees out sick, they're on vacation, they've been pulled somewhere else. Having the ability to kind of look into the future with this from what we currently have will be really valuable in helping decide what's the best thing that we should be doing to be in the best possible spot down the line.
Next, we will talk about the condition-based maintenance. And first of all, what is condition-based maintenance and why is it important? Condition-based maintenance is a maintenance strategy that monitors and collects information on the actual condition of machine's health and recommends maintenance decisions based on such information. Under condition-based maintenance, maintenance should only be performed when certain indicators show decrease in performance or upcoming failures. And compared with the preventive maintenance, condition-based maintenance increases the time between maintenance repairs because maintenance is only done on an as-needed basis. And we use the printed circuit board assembly model from Smith and Sturkos books to implement condition-based maintenance. In the PCB assembly model, board first arrives at the placement machine from an upstream process. Then a board will go to one of the 3 fine pitch stations, fast, medium, and slow, whichever is available first. After that, boards are inspected and categorized as either good parts, bad parts, or some of them need a rework and go back to the placement machine, and with corresponding percentages. And we note that the inspections part and the rework part, they are processed based on the worker schedule. And since the inter-arrival processing, inspection, and rework times, they are all random, we expect the queuing in the system. And for illustration purposes, we assume only the placement machine part will encounter failures, but the rest will all, there won't be any breakdowns. In this model, we simulate the rework percentages to replicate the deterioration of the placement machine. And specifically, we assume it has an initial value of 0.1 and increases by 0.001 every hour as the total processing time of the placement machine increase. And there are also some randomness to mimic the real deterioration process. And we assume when the rework percentage reaches 0.2, the placement machine will break down. As is shown on the in the plot on the right-hand side, the horizontal axis is the total processing time of the placement machine measured by hour, and the vertical axis is the rework percentage. And starting with 0.1, we can observe that the rework percentage keep increasing, but there are some randomness. And on average, the rate is about 0.001. And since we cannot directly observe the rework percentage in the real manufacturing process, we need an indicator to monitor the machine's health through the quality of the life, the quality of the product's life. And the indicator we use is the number of rework products per day. And whenever we observe a substantial increase in the number of rework products, it implies a severe deterioration in the machine's health, and therefore the maintenance is required soon. Here is the dashboard of our model, where we can see the metrics on the left-hand side and the graphs on the right-hand side, and they are showing, they are presenting in a real time. So this is the Simio model we built for the condition-based maintenance. And let us start the simulation right now. So we can see that the boards first arrive at a placement machine and go to one of the fine pitch station. And after being inspected, some of them need rework and go back to the placement machine, and the rest are categorized as good or bad parts. And we can also see that the real-time metrics shown here. Let's zoom in a little bit. So it shows the current date and time in the Simio model. And this is the current placement machine processing time, and this is the total, the cumulative value. And we can see as the placement machine processing time changes, the rework percentage changes as well. And here we also keep track of the number of rework per day and the total number of rework products as well. And more intuitively, we plot the rework percentage and the number of rework products per day in real time. So in this rework percentage, we can see starting from the 0.1 initial value, the rework percentage keep increasing on average, but there are some randomness there. And let us now speed up a little bit just to show the different trend of the number of products per day. Okay. So right now we can see the number of rework per day. It increases on a daily basis and reset to 0 at the end of the day. So with the randomness and also the different processing time and the percentage change, the value of the number of product per day, it varies a lot. But on average, we can see they are below 27. So we can think of that is the typical value, and there won't be any worries. However, as we can see around January 11, there's a substantial increase where the number of rework products reaches almost 35 or 33. So this is the point that we think that there's a severe deterioration in the placement machine. So we need to watch out to implement the maintenance as required. Previously, we also simulated preventive maintenance and corrective maintenance. And for the next step, we are planning to incorporate condition-based maintenance into the overall maintenance strategy. And we will simulate and analyze the condition-based maintenance strategy to check their impact on the placement machine throughput and time in system. And we will also determine the optimal threshold of indicators, such as in this case, number of rework products per day, and that maximize the above performance measurements.
Okay, so what Sylvia and Zhouyi illustrated or demonstrated was kind of this conceptual idea of how Simio can be used within a digital twin environment to help with decision making, whether you're talking about with maintenance or with production or with inventory or scheduling. And obviously this is still work ongoing, and we're still working on developing and applying it to the manufacturing company's actual production systems. So a lot of this is still in the conceptual phase. But what we've also done is started thinking about, okay, how does Simio fit within a whole kind of digital twin architecture? So this is kind of our conceptual view of how it could work. So over on the left-hand side, you'll have a lot of data coming in from live streams. These could be 3D images, these could be machine sensors, some sort of production schedule, ERP, and then over on the right-hand side, we would have the digital twin, which would be this real-time representation of what is going on in the production. And some of this could involve, different types of ways to view the information, whether you want to view it in a 2D environment, whether you want to view it in a virtual reality environment. And then we need analysis behind that. So for instance, using the simulation then to determine, okay, given this is where we are currently in the production situation, here are problems where we might be seeing. How does a production look like over the next 2 weeks, over the next 3 weeks? And that's what Simio can do for us. And then also Simio, as you know, has a lot of nice scheduling and optimization tools. So then can we also use that information to optimize and help us figure out what the best decisions are regarding the current state of where we are going forward. And so that's kind of our overall vision of what a digital twin could look like for this manufacturing company, and how the different pieces can all fit together, including Simio, which will have a large role in it. And part of what we also want to think about within this context is, so if we have Simio and the user is able to click on Simio and run certain things based on the digital twin, what type of information should they be viewing from the Simio output? And how does that information combine with the real data? So there's some information that will be real data from the production floor. There's other information that will be simulated data from Simio. There's other data that could be just kind of numerical analyses. And so how do we kind of put all of this together into some sort of dashboard or some sort of user interface that makes sense? And that's also something else that we are working on as part of this project. Okay, so that kind of gives you a sense of where we are. As I said, this work is ongoing. We're still working on this, and our Simio piece is only a part of a larger project that we're doing. But we think we've made some useful strides in thinking about, okay, how do we actually simulate from a current production status, and then use Simio to help forecast what these bottlenecks and solutions could be. And then how also can we use Simio to help us think about condition-based maintenance? Can we set up a simulation of the production where we're gathering information from a machine as Zhou talked about, and then determine when to do maintenance based on the health of that machine, and how can using a discrete event simulation help us do that. As we talked about and try to emphasize repeatedly this presentation, our desire is really try to help these digital twin concepts with decision-making on the factory floor. And we think Simio can help make that connection as well. And then obviously integrating this simulation with other components of the digital twin, as I talked about earlier, such as real-time tracking, how to display information, as well as some of the cool things about using virtual reality and artificial reality. So with that, I'm going to stop. You can see our emails down below. Please email any of us if you have questions or you want further information, and we'll be happy to answer questions as well as part of the Simio Sync conference. Thank you very much for your time, and look forward to talking with you further as part of this virtual conference.
All right, hello, and thank you to the Iowa State team. We only have just a few minutes here for questions, so I'm just going to jump straight into it. We have a question here on, is the model currently being used by the company to make any decisions? I know you mentioned it's an ongoing process, but is there any use being done today?
Do you want to talk about that, Sylvia?
Sure. So there is, we've given a version of the model, not the one that I was showing in the presentation, but there is a version of the model that's been given to the company that I believe they are using. I haven't received any feedback from them about how it's working. I don't know if you have, Dr. McKenzie.
Not specifically, but yeah, my understanding is that they are using that part of the model that Sylvia was talking about. Mm-hmm.
Okay, great, thank you. You talked about the possible variations in worker availability. Are there any other aspects of the model that include variability or reliability logic, and how were those implemented?
So
go ahead, Sylvia.
All right, yeah. So yeah, we've got the worker availability. There is also variability included in all of those process times. So that's actually a parameter in the model that the modeler can change. You can set that to be whatever you would like it to be. And we actually did a little bit of previous work trying to figure out what effects different variation levels would have on the model, because the company didn't know right away what that variability level that they had was. So we did a little bit of work trying to figure out, okay, if it's this, what does that look like for the model? Okay, if it's much higher than that, what's that going to look like?
Okay, yeah, that makes sense. Okay, I think we have just time for just one more here, and I think you touched on this towards the end, but maybe if you could just elaborate on what makes this model a digital twin compared to just a traditional simulation model.
Yeah, so we view a digital twin as essentially a real-time image or representation of what is actually going on the manufacturing floor. So usually you do a simulation and you build a model and you simulate and you say, okay, what if we do this, this, and this? But it doesn't actually, although it doesn't actually always incorporate what is actually going on at that moment in a manufacturing setting. And so our goal is, how can we actually use Simio and use a simulation to capture where we are exactly in the manufacturing floor, and then simulate from that point going forward.
Great. Okay, yeah, that makes a lot of sense. Thank you for that clarification. Well, great presentation, you all. Thank you all for the Q&A as well, and thank you for being a part of Simio Sync.
Great, thank you.
Have a good one.